Okay, molecular geometry. Examples. So we know that Vesper tells us that molecules will assume a certain configuration based on the central atom and how the atoms attached and the lone pairs attached to the central atom can influence the geometry. Let's do an example of CO2. Today what we want to do is determine whether or not a molecule is polar and what makes it so. Well, CO2 has 4 plus 12, 16 electrons to work with. Don't forget it's the group number and then the number of atoms. So 1 of 4 and 2 of 6 is 12, 16 total. So then if we decide which one goes in the middle, you would guess it'd be carbon, you'd be right. We'd have our oxygens left and right. We put in the bond pairs. Then we complete the octets of the surrounding atoms. Don't get hasty with the double bonds until you're sure that you're going to need them. So because carbon only has 4, we're going to need to get 8. Maybe you recognize the fact that we're going to move 2 pairs from the oxygens, 1 on each, into that central atom. So we'll have a double bonded carbon to an oxygen on each side. Now the question is this molecule polar or is it not? The first thing you need to do is establish whether bonds themselves are polar. And to do that, you recall, you're going to use the electronegativity differences. So if you looked at oxygen on the periodic table, that's 3.44. Carbon is 2.55. And that should make a difference between the two. That difference is going to be about 0.89. So that tells us that the bond between carbon and oxygen is going to be polar. Since we have 2 of those bonds and they're in opposite directions, look what happens to the dipole. This is called a dipole. That dipole tells the direction of polarity. The arrow points to the more electronegative element. The plus sign on the back is the lesser electronegative element. So carbon in this case is more electropositive, oxygen's more electronegative. Now looking at this, you can maybe envision a tug of war. You got 2 substances, 1 on each side. They're equal in their magnitude of strength. So they're pulling in opposite directions. And that's what I like to view. I say, look at the central atom. And if we were to just examine its movement based on the pull one way or the other, if there's a net pull one way or the other, then it's going to be polar. In this case, it's canceled. Those 2 cancel one another, and that cancellation leads to a nonpolar molecule. Some of you have been asking, how do we make double bonds? Well, you might notice in the molecular model kits, you've got these flexible sticks. So taking the flexible sticks, you can put them together, and they can then represent an atom of oxygen and an atom of carbon stuck together. Okay, and then if you do the same thing on the other side, you would again find that you have another set of flexible sticks, 2 of them, and that makes your double bond. See, you've got 2 pairs of electrons are being represented by those flexible sticks. So that's CO2. All right, let's try another one. We're going to do ammonia. Ammonia has the formula NH3. Again, take it step by step. It'll be easier in the long run. 5 for nitrogen. 3 times 1 is 3 for hydrogen, total of 8. We'll put our central atom in, N. Surround it by the hydrogen atoms. They always go to the outside, and they're lower in electronegativity. Now, I could put them up in the corners of a triangle. I could start that way, and that would be fine. So I put in my pairs. I have 6. I have 2 extra electrons. I'm going to put them on the central atom there. Now, here's the part that's important. These electron pairs have forces that they exert on each other. They're the same charge. Bonding pairs and lone pairs both have negative charge. So negatives are going to repel each other. They're going to try to get as far apart as possible. So that's going to lead to the structure that's going to be best drawn like this. 3 H's, 1 N, and we've got a lone pair. You see the lone pair here on the nitrogen, that is repelling the other ones. So much so to the extent that when you make the model for it, if this in the center, that red is nitrogen, you can see that these angles would probably be a little bit more than 109.5 actually. They would be bent a little more so because that lone pair, the lone pair is going to repel to a greater extent than bonding pairs. That's a bit more than we need to know right now, but that is plenty sufficient to help us out. Okay, so if we were to draw that in 3 dimensions, remember CO2 is linear, so there's no point. But in 3 dimensions, remember this is going to be a tetrahedral class, And I believe we're looking at a pyramidal shape, something of that nature. And so we're going to try to draw this in 3D, and you might see it then as maybe we put the lone pair in the plane with one of the hydrogens, okay? And that means there's one H going back and there's one H coming out, so I need my staircase for the H going back, and I need my wedge for the H coming out, and so now I see that this is more like a pyramid shape. You can actually envision, right? These aren't bonds now, they're just meant to represent closing the sides of a pyramid, so you can see maybe now it's got that pyramidal shape to it, which is kind of interesting. Okay, question, is it polar or is it not? So what we need to do is look at electronegativities again. Hydrogen's about 2.2. I think you're looking at nitrogen as 3. I think it's either 3 or 3.06, something like that. I'm going to call it 3.06 for lack of a better description, which gives me a difference of 0.86, right? So the difference in electronegativity is 0.86. That tells you that it's a polar bond. Okay, question, which way does it point? If I draw my, like I did in the CO2 example, if I draw my dipole, it's called a dipole. If I draw the dipole, which end gets the negative and which is the positive? Well, n's bigger, so I draw a dipole towards n, and I got to do that 3 times. What about the lone pair? The lone pair does nothing for a dipole. It's simply an extra negative charge. In fact, you can think of it as like a pinnacle or a crown on top of this molecule. That's just a bunch of negative charge. So now if I look at the 3 hydrogens, they are pushing in on that N, and there's nothing balancing it. So here's my NH3. I look at it as I'm pushing in here, pushing in there, pushing in there. There's nothing to balance it. If I had another one up top, that would push downward and effectively cancel part of the force of the bonds of these other 3 corners. So if it's symmetrical, you look at it symmetrically, if all the atoms are occupying those 4 corners, then it's going to be probably nonpolar. But since we have a lone pair up top, that's extra negative charge, therefore this is going to be a polar molecule. The overall polarity can be shown with a giant dipole. It's basically the sum of the addition of the rest of them. So if I draw it like this, now it becomes very clear which end is positive and which end is negative. It's the underside here, and it points up because you add all of those together. It's sort of like the net direction that that force would be applied, okay? So the overall molecule then is going to be polar in its nature. Okay? Let's try another one. Symmetrical molecules, I just said, if they're all in 4 corners, it could be nonpolar. But what about CH3Cl? All right, we do our count there. We've got 4 from the carbon, we've got 3 from the hydrogens, and we've got 7 from the chlorine. Add those together, you get 14. What goes in the middle? It's not going to be chlorine, it's going to be carbon. Carbon goes in the middle. Then we put an H, an H, an H, and then a Cl. That's the most plausible structure. For reasons we'd have to show math, but it's okay. All right, so then pairs in for the bonds. There we go. That's that step completed. Now we complete the octet of the outside atoms. H is already good, right? It's got 2. So now we're going to put the other 6 around the chlorine, and we're done. That's 14 electrons. If you put it into ABE notation, AB4, which is tetrahedral, tetrahedral. I know that's getting old. I know that's getting old. But it's tetrahedral, tetrahedral. Okay? 4-sided pyramid. However, this time we've changed the atoms. Does it make a difference? You bet it does. So here it is. CH4Cl. I'm using red for carbon. Doesn't matter. Doesn't make any difference. Green is for the chlorine, and the white ones are going to be the H's. Okay, so we draw the picture of it. It doesn't really matter. But let's do this. I'm going to put the carbon here, 1 H up, 1 Cl down here, and then I got 1 H going into the paper, and I got 1 H and a wedge coming out of the paper. Okay, so now we're looking at electronegativities, right? Because we want to say, is the molecule polar or not? Well, electronegativity is 2.55 for carbon, and let's see, that's 1.6, I think, for chlorine, and the hydrogens are 2.2. Differences between the hydrogens and the carbon, 0.35. From the carbon to the hydrogen, it's 0.35. Those are nonpolar bonds. Nonpolar bonds. We might be tempted to call it a nonpolar molecule. If this H was in place of the Cl, it would be a nonpolar molecule. I think we showed that today in class or yesterday. But because it's chlorine, it's different, see? Because the delta from the carbon to the chlorine is different, that is going to be, what, 0.45, 0.55, 0.61. 0.61 is going to make that a polar bond in favor of what? Well, remember that the arrow always points towards the higher electronegative element. So that arrow goes that way, and we put a plus sign where the carbon is. Okay, so automatically now we're setting this up to have two ends, right? The negative end here towards the chlorine and the positive end where the carbon is. That is a polar molecule. So this is polar. If you had to draw an overall dipole, it might look like this. There's only one arrow to follow. Plus goes on the end of carbon on the back side here. Back here points all the way through this chlorine to the other end. So negative end, positive end, two ends of a sphere like the poles of the Earth, hence you're going to call it polar. Last example. PF6 minus. Okay, what does a negative sign do or a positive sign? That influences the total number of electrons. So remember, if it's negative, you're going to add. If it's positive, you're going to subtract. So phosphorus has got 5. 6 fluorines make 42 because it's in group 7. Whoops, not multiply, but plus. And then the extra electron means we add 1. So it's 5 plus 42 plus 1, and that's going to give us 48 electrons total. Now, it seems like a lot. We'll draw it. Here's P. Fluorine, 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 there's 6 of them. Okay, and then bond pairs. Remember, phosphorus is okay with 12. It can violate the octet rule because it can expand its octet with its d orbitals. Put the lone pairs around each of the fluorines, complete the outside octets. Okay, we add them up. That's going to be 6 times 8, which is 48. That gives us our total. We've done it correctly. That's AB6. And AB6 is octahedral. Octahedral. I know. Okay. So then the only other thing would say put square brackets around it because it's got a -1 charge. Overall charge is -1. So what do you do for that? Well, we need to have something that's going to be able to accommodate a total of 6 bonds. And I think that the beige ones or the tan ones are going to be able to do that for us. And we're going to put that around here. And we're going to make our octahedral structure. The bond angles are going to be 180 degrees for the not the equatorial, but the axial H's. So the poles, if you will, of this thing, top and bottom. So here's our poles, here and here. That's 180 degree. We have 90 degree on the equatorials, and then we have 90 degree from the axial to the equatorial. So there's 2 different 90 degrees, and then you have 180 degrees. If you were going to draw that, there's lots of ways you can do it. But one way that I would like to do with this one is to put, say, the phosphorus in the middle, of course. I'm going to have a fluorine up. I'm going to have a fluorine down. I'm going to have a fluorine going back on that end, fluorine going back on this end, wedge out the front, wedge out the front. And technically, we'd want to put square brackets around it because there's 1 extra electron in there. And now we can say, well, what about the bond polarities? Is it going to be polar? Probably. Fluorine is the most electronegative element. It's 3.98. If we were to look at phosphorus, I'm quite sure it's less than carbon. I want to say it's on the order of 1.9 or 2. Not having a book in front of me right now, we'd have to look that up periodic table-wise. Let's see. Well, that's going to be a bit of a challenge here at the moment. Oh, wait a minute, phosphorus. I can see if I can find it here in a different book. Phosphorus is 2.1, fine, 2.1. So we look at the difference, we call that 1.88. So the difference in electronegativity is 1.88. Now that typically is ionic, right? Well, yeah, mainly ionic. There is some covalency towards it, but we do know that the electrons are being pulled towards the fluorine. So looking at them, we'd have dipoles drawn, to each of the fluorines from the phosphorus. Okay, here's the part that's going to make it a little bit easier. All the atoms are the same. So this fluorine and this fluorine are opposite. They pull opposite direction. Cancel. This fluorine and this fluorine, opposite directions, cancel. Top fluorine, bottom fluorine, opposite directions, cancel. So because none of them shows a net dipole, we're going to call this nonpolar. Even though the bonds are polar, the overall molecule is nonpolar. You can make this polar very simply. If I changed one of those atoms, and I made that an H, or a bromine, something like that, because I changed that structure, those dipoles no longer cancel in the same way. Therefore, that would make it polar. But as it stands with PF6-, it's nonpolar. I hope that's helpful.